cleansing exercise. So there you have some chemical agents. We've done some experiments with physical agents like the UV or the temperature, different temperatures. So this is more about the control of like bacteria in the industry, in households, in hospitals. So it'll just give you an idea of what is used and how they differ in their modes of action and how successful they are also. So you have physical, chemical, and mechanical methods to destroy and reduce undesirable microbes. And this list is including pretty much everything we've talked about. So you've got vegetative bacteria cells and endospores. So here you've got prokaryotes. You've got the fungi, trying to control their spores, also yeast. You've got protozoans, worms, viruses, and prions even. So you've got pretty much everything. We're not really controlling algae, which you've looked at yesterday, quite a few, because we've talked about how they're usually autotrophs, so they're not really a microorganism we're concerned with when it comes to undesirable microbes in an environment. I mean, we talked about it yesterday, I think, and I said I find them regularly in our water filter when we haven't cleaned it out. So that's how.
Wait, what happened?
If you have a water filter and it sits around for too long, it starts getting green.
Oh.
It might be good for you. I don't know that yet, but it's interesting because we've for example, when they build those aquaculture systems where they rear the fish, everything is black and everything is covered, and I always wonder about that. And it's mainly to keep algae out. So it's not that you want to keep them out because they could be the beginning of growth of other organisms, etc. But they're not really the big concern. But they are really successful in inhabiting wet or mostly wet surfaces or water containing water containers. So you're always trying to keep it as dark as possible and to make it impossible for them to successfully inhabit whatever you're working with. Could also mean I should maybe darken my water
There was this
filter.
like beauty salons that I went to that they had one of those water dispensers with the 5-gallon thing on top, and it would turn green. The water would turn green, and even though they bought it from like one of those companies, so
they had it a long time up there, you think, or it had to be?
I don't know, but I mean, you would think that it would come like pretty purified.
Yeah, and especially because they're closed, they're usually upside down.
Yeah.
Yeah.
So what was the solution?
That's worse than my house. That's all I can say.
Cover it?
Well, that would prevent it from happening, I'd say, but I wonder how they even get in there initially. That might be the overall conditions, where you don't know if you attach it to, say, I know that they have these standing ones. If you attach it to a dispenser, there could already be a little bit of growth in there. Usually, it should be clean for sure. But it's the overall conditions. But you don't make any conclusions about my house. That's the only thing that's dirty. But that's the only thing I can think of.
They put a little bleach in it.
Yeah, they did?
No,
well, yeah, you would probably want, there's the question of what's worse, having a few algae in there or the bleach. But you could basically just bleach the whole system once and then you'd be fine for a long time. I never seen them in those water dispensers.
Maybe
ever.
call the company and have them change it out.
Right, call the health.
I know,
Get the
see,
soccer.
and now, see, can you come get?
Call the,
I don't
health
know.
department.
Oh.
Hey, they'll-
Because we got one at our work and I think it was like super
All is clear.
Yeah.
I've never seen one green, I've changed out a lot of them.
Yeah, you changed a lot of them?
Right,
That's it.
Filling in
What is
a
it?
gap at that company, they're just filling themselves in the back.
Oh, it could be.
I know, just don't drink that water, no.
Water, okay.
Yeah.
So talking about disinfecting, sterilizing, and et cetera. So this is a table, and don't worry about the small writing because you're not, it's in your book. But basically, we talked about, I just introduced physical, there's physical, chemical, and mechanical. And usually the main thing you want to do is, if you disinfect, or try to remember the differences between those three. And mainly, if you disinfect, you get rid of the vegetative pathogens, so the vegetative cells of bacterial cells. But you usually don't get the endospores. So disinfection is a little bit less stringent, I guess, than sterilization. And then in sterilization, that's where you get pretty much everything. And there are certain procedures that are, for example, applied in the back room here that make sure that everything that goes into this red bucket here is being completely sterilized. Or even your tubes, all the tubes we're using, all the cultures we're working with, although they shouldn't contain anything too dangerous, they're completely sterilized. So you have to find methods to not only get the vegetative cells, but also the spores, the endospores. And then antisepsis means against septic conditions or sepsis, against sepsis. So that would mean if you have a body, it's applied to a body surface. And usually sepsis means your body is having a reaction to pathogens or to bacterial infection. So you're preventing that with antisepsis, and it's usually applied to the body in this case. So clearly, you wouldn't use a lot of disinfectants, for example, on your skin, because a lot of times what destroys a bacteria can also harm you. There's very powerful sterilization methods, and a lot of times you can't even apply those to certain products. Like say you want to clean food products, etc. You wouldn't do that because with sterilization you might change the taste of the food or the character of the food, so you can't use those either. So there's different applications for those three. But just keep in mind while we're going through those slides, you're always trying to, or it's important to determine: are we sterilizing, are we disinfecting, or is it just an antiseptic agent? And so the highest resistance, and you already know that now, is in general bacterial endospores. Those are the ones that you're always concerned with, and then and those are the ones we've talked about a couple times, that you can find millions of years later. So they're able to resist environmental conditions, dry. They're actually produced in those conditions, and then they can survive those conditions, dry conditions, hot conditions, a lot of pressure. So they're almost indestructible. And so that's where the highest resistance lies. And then you have some moderate resistant organisms up here, and then some down here. You don't have to memorize which group they've, just so you know there's differences, and on the highest, really where we have the hardest or the biggest problems is with the prions and the bacterial endospores, which is interesting because those really are the proteins. So you would imagine they'd be easier to destroy, but they have some of the highest resistance. And there's going to be a few tables in here that you can find in your book. They're just in there, so you can go back if you're interested in something specific, but they're not. I'm not going to talk much about them. This one is an exception because here you can look at just the differences if you have the resistance of, or it compares the resistance of endospores to the vegetative form. So if the vegetative form is eradicated at 80 degrees Celsius of moist heat, then the endospores are need a higher temperature, and we get to how you can achieve that temperature. So it's a factor of 1.5 going from the regular cell to the endospore, and if you use radiation, for example, or gas, you can see that those factors are they differ, but basically it differs in the in the temperature or in the amount of, or in the time that you have to apply a certain agent to kill to basically create sterile conditions.
The group or aldehyde, that's a liquid?
I don't know for these little liquid suicidal. I don't know which one that is, what compound that is. Because then you would 10 minutes would be pretty. You could imagine that you can apply that. That would actually be pretty long for that. I'll look it up. I'll let you know throughout the or a little bit later when we start with the other with the practical part. So we've already talked about this. So sterilization, again, all viable microbes, including endospores, including viruses, including prions. Disinfection. You destroy the vegetative cells, but not the endospores, and usually that's applied to surfaces and tools, surgical equipment, antiseptic directly on the body surface. Those are just so you can distinguish those three. And then sanitation just basically means you mechanically remove microbes, cleaning, and there's different ways. There's a table that shows you what kind of sanitation methods there are. In degermation, through mechanical means again. So you basically, use a wipe, for example, to clean surfaces. So these are the different. Shows you the, for example, what sepsis is, the growth of microorganisms in the tissue, and asepsis. Antiseptic chemicals, and then all the different terms. But just so you have the basic understanding of what it means to sterilize a liquid or sterilize something in comparison to disinfect something, or applying aseptic or antiseptic chemicals. So mostly what you're trying to do is to eradicate or to completely destroy any kind of microbial growth, in depending on where you are, say for preparing surgical equipment, things like that. But it's hard to know how successful you are in general, and you've seen it here in the lab. There's a lot of situations where we are. You realize how much contamination is going on. What you're really trying to do is create a permanent loss of reproductive capability of the organism, even under optimal growth conditions. So even if you use, say, a surgical instrument again, and it's under conditions where it would be growing really well, that wouldn't happen. So you're making sure the cells and the endospores are the possible endospores are destroyed and aren't able to come back or revive in optimal conditions. And so clearly that has to do with the number of microbes you're dealing with initially, and that's always important. You know, if you hear about a microbe and you hear about it being part of your natural intestinal flora, for example, and then you read about it or you hear about it as being a causative agent of, say, some disease, a lot of times the difference is where in the body this agent is, but also the amount. So what you're exposed to, a lot of them, the soaps we're using, they're not really that effective. You wouldn't kill everything, and then you talked about that yesterday too. You come out of the bathroom and you grab the handle and you wonder what's back on it. So it's really exposing yourself to less. So the initial number of microbes is important, and there's a few slides about how that affects the death rate and how it affects the time it takes to kill everything or to kill most of the microbes. The nature of microbes in the population. So do you have what's the mixture? What kind of microbes are you exposed to? What temperature and pH of the environment you have? Because we talked about the different conditions, environmental conditions that they thrive in. So that makes a big difference. Are they in an environment that's perfect for growth? Important also, just like the concentration or the amount of microbes is the concentration of your agent, how it actually works, and if there are any other solvents, inhibitors, organic matter. So, is the microbe on a surface exposed to what you're doing, or is the microbe solved in a liquid, or is it in feces? It's going to be much harder to actually kill everything than if you have an exposed, have the culture or the microbial mixture exposed. So those are just the statements shown in graphs. So if you have, it obviously depends on the length of the exposure. So if you have a huge amount of cells up here, 10 to the 9, and you start exposing it, and that's just a general graph. It doesn't apply to a specific chemical or a specific, or it's not, this graph is not specific for a chemical or a physical method. It just means you have a high concentration, and you need, over time, you get to sterile conditions, and there are certain guidelines where in an autoclave, it's clear, it's been determined what this time or the length of the exposure has to be to end up at zero, and then you probably have a little bit more time to make sure you're on the safe side. The microbial load, so if you start with more, here you have again the growth, you start with more, and you compare those two. Here's the low load and here's the high load. Then obviously those curves or lines run parallel, and you need less time for sterilization. Here you have the main difference between the vegetative cells and the endospores. So the resistance of the vegetative cells is much less than the spores, so you get a result much more quickly. And then finally, if you use, we've yes.
What's an example of a microbe bistatic versus like a microbe bistatic?
We had those in. If you look through the table, remember the hand cleansing agents we used. There's some, the milder ones are basically static, meaning keeping, stopping the growth of the microbe, but they're not actually killing all the microbes. So you're keeping the population, and you can see that here. You keep the population basically at a certain level. You're not you change the conditions so growth is not exponential anymore. You're basically keeping at a certain level, whereas in the cidal agent, for the micro biocidal agent, they're killing, and so you basically start dropping the population down to zero. So those are much weaker. The hand, what's the name for the? Yeah, that for example would be a static one. And I think in the table it tells you, the table that is posted on the laboratory, it tells you which ones are which are which, so which belong to which category. And usually that's a give and take. Again, you obviously want agents that kill the microbes, but you also don't want to expose yourself to too much to conditions where it affects you. So you always have to find a compromise between the two. But I think alcohol-based ones are the ones that really are the most effective. So it's another. This just is a set of questions you would ask yourself when you try to figure out what am I going to use. So the practical concerns, and you would probably make that decision at home all the time. You know, what do I want from it? Is it necessary to sterilize something? Does the item have to be reused? You'll see that along the next few slides. What can you actually apply? Like I said, you have maybe you try to prevent fungal growth on food. So food processing is probably where this is really big. And so you just harvested say fruit, and you want to apply some kind of growth or some kind of control of microbial and fungal growth, but then at the same time you don't want to change the appearance, or you don't want to change the taste or the characteristics of that fruit. So how much can you really do? What kind of method is ideal for that? So is the method suitable? Is it going to penetrate to the necessary extent? And is it cost and labor efficient? So is it safe? Is it something you can apply? And they're constantly working on this. This is not something that's all established. I think they just came out. I read in an article about they just came out with maybe some other agent that has characteristics, or they have to be approved just like everything else, but they come out with new agents all the time, trying to figure out how can we increase the characteristics that we like, while not while being as safe as possible. So it's an ongoing process to figure out these different methods. But there's some established ones like we're using here that make sense once you understand how it works, and so they were not going to change. So how they work in the how they actually work in the microorganism, or how they affect the microorganism is usually there's a few possibilities. So they can affect the cell wall, and they can actually make the cell wall fragile, and then the cell lysis. So you have some examples here of alcohol, for example, is we just talked about hand cleansing agent. It can affect the cell membrane, so the membrane loses its integrity, and surfactants are important ones. They lower the surface tension, and if you look here, so the surfactant basically is able to infiltrate the membrane and become part of this membrane basically, and then that disintegrates or leads to disintegration of the bacterial membrane, and then by losing control over in and out, the cell dies. You
Are
can.
they able to target those, or does it work on all membranes?
That depends. You know, there are obviously big differences between microorganisms. So you can't assume that if it works on one microorganism, it works on all of them. There's definitely differences there, but they're not targeted in terms of being able to bind specifically to a membrane of one species and not, or one strain and not the other. What you can also imagine is, and that's more specific, is that you know, there's, so basically you have the cell wall as a barrier in the cell. You have the cell membrane, and then you have always important proteins and nucleic acid. And so if proteins and nucleic acid synthesis is affected, there's problems with replication, transcription, translation. So all these processes from the nucleic acid down to the protein synthesis are changed. And so you can do that by, say, UV light. That was one of the methods we used. Formaldehyde, we'll get to that later. So there's compounds that affect protein and nucleic acid synthesis. And then some go directly to the protein and they disrupt or denature protein. So you don't go through the protein biosynthesis process where you affect the synthesis of proteins, but you affect proteins directly. And that, I think, is shown in the next one. So you've got alcohols again, acids, heat, phenols also. We'll get to that in a little bit. And if you look at a protein, remember the different structures we talked about, and so that would be the native state, and you have the enzyme, you have an active site, and complete denaturation would mean, you know, if you apply enough heat or the pH changes, you can find basically the three-dimensional structure completely getting lost or being lost by the protein. And obviously you would assume that this protein is never gonna, this enzyme is not gonna do what it's supposed to do. It can through heat or pH change can just change the shape so that the substrate won't bind anymore. And I think we've talked a little bit about how specific those enzymes are. So they have an active site, and that active site is very specific to a substrate. So small changes can already change the shape so that it won't accept the substrate anymore. And then you can also block the active site. It's kind of like almost like a competitive action, but and it's done by heavy metals. A lot of times we get to those at the end of the lecture too, but that's one other option. So just keep in mind that the change in the protein structure is one of the ways, and it could be, it doesn't have to be as drastic as completely changing the shape of it. Small changes are enough, or blocking the active site of the enzyme. So those are ways to control the proteins or destroy the proteins in microorganisms. So we'll talk about physical and then chemical, I think, and then maybe some mechanical, mainly physical and chemical control. And so you have heat, which you can have. It can be dry heat or moist heat, and I'll tell you what's more desirable and what's and why. And then you apply cold temperatures. You use your freezer and your fridge to elongate, I guess, or to increase the duration of all your food products. Desiccation means drying, so you can basically remove most of the water, which is one other method to control microorganism growth. Radiation, we tried that over here. I get to that too. and then filtration. And filtration is going to be interesting because to me, the lab I sometimes go to is an engineering lab, and they do a lot of filtration, and it's amazing the cost of filters. And filtration to me is like the smallest filter I know is probably a coffee filter, and it's pretty obvious. But you can design those, or they are manufactured so specific that they actually are able to filter out microbes. And you have them in buildings, in hospital buildings, and they're able to filter a lot of the microbes out where you would imagine that that's impossible just knowing what size they are. So the big difference between moist heat and dry heat is that this one works better. You need lower temperatures, you need shorter exposure time, and the denaturation of proteins is happening at a better at a more desirable rate. And you do with dry heat, you also get that, but you need higher temperatures. So you can actually, what you're doing in your when you, for example, apply, I would say, dry heat by putting your inoculation loop into the flame. If you go to the inner part of the flame, you might get 1800 degrees Celsius, and so that would be dry heat, and you're definitely burning off whatever there is. But you can imagine that if you want to apply that to other in other areas, it'll be really hard to apply a heat like that. So you could, if you're done with an experiment, if you're done with whatever you wanna, if you wanna just make sure whatever you worked with is sterile, you can pretty much burn it, and that's what happens in some of those in some applications. But you can't do that. You can't afford to use that much heat. So moist heat is just happens at a lower temperature and a shorter exposure time.
Why?
That's next. So mainly, if you look, and this is just a comparison I'll show you. You have for moist heat you have 121 degrees Celsius for 15 minutes. You would need 10 hours to do that under dry heat. So you can imagine that the difference just in energy that you need for these two makes a big difference. And so if you go out and, for example, apply it in an autoclave, you would go and you would try to get moist heat up to maybe this temperature, and after 10 minutes you have sterile conditions.
Like a dishwasher's moist heat, right?
Yeah. I wonder if for the dishwasher that has a lot to do, because you're not creating sterile conditions in there, and you wouldn't need to. I wonder if that's probably just a side product of using water and detergent to clean. Just like you would say, well, if you go to the sink and you wash your own dishes, you're probably going to use warm water and detergent and not cold. Just removes whatever you want to remove off your plates better. But I think has less to do with might add or might help, but it has less to do with actually wanting to create more sterile conditions. So mainly what you need is, or where the heat comes in is, how endospores can withstand dry conditions for a very long time, and they can, most adverse environmental conditions can be survived by endospores, but dry conditions are one of them. And mainly, I think what it is water is. I said that before too. If you have microbes, usually even in dry conditions, if they're vegetative cells, they have a little bit of film of water. So water is important to keep any organism alive, and that includes the microorganisms. So what they do is in dry conditions, in absolutely dry conditions, they build endospores, they produce endospores, and then survive that time until the conditions change. So that's one of the that's why you need for that feature, for those endospores, is where you need really high temperatures above boiling to kill those. And to kill them at a specific temperature would be, you measure the time, how long it takes, and so that would be the thermal death time. What's the length of time required to kill them, and then the death point would be the lowest temperature. So you're just looking at how long do I need and what's the lowest temperature, because it's all a question of, how what you can get away with, because it's hard to get these conditions to kill microbes.
Okay. For the moist and dry heat, so the moist heat pretty much prevents the endospores from forming, and then it kills them at a vegetative state, or because when it's...
No, I think in general, if you have water, if you basically conserve. You usually, if you think about it, you conserve things by drying them, like dried fruit, or so you're taking the water out. So water usually helps to first of all heat up. It absorbs the heat, so you can break and you can denature proteins faster, etc., etc. So that's where water makes a big difference.
Water has the highest boiling point, right? So probably kills except heat a lot.
Yeah, and the main thing is, the problem is, and that's where the autoclave comes in. If you boil water, so if you already if you see that that was in the last one, I think, but at 100 degrees Celsius, and I think that's on the next slide. So if you have you have water at 100 degrees, what happens? Like what happens at 100 degrees Celsius with water? It goes from the liquid to the gaseous state. So that means if you have water vapor from boiling water, it's 100 degrees, and it's never going to get higher. Like how would you increase? And the only way the temperature of the water vapor, because it is 100 degrees and it's not going to go up. So basically, I know I explain to me usually that you have a liquid, and the energy needed to go into a gaseous, I just do it like this, state, so you put energy and heat energy, and you create a gas, and that's at 100 degrees Celsius. So the only way you can get a higher temperature is by putting pressure on. So there's more heat absorbed before it goes into the steam state, basically. And so in an autoclave, you put the steam under pressure to sterilize, and that's really in an autoclave you have you create pressure situations so that the steam goes up to, the water steam comes up to 121 degrees Celsius. So I'll go back real quick. You would be here, and you do that by applying 30 psi. It's probably what you have in your car tires, but it's I think 15 is what you have. 15 equals 1 atmosphere. So if you're on sea level, which we are probably, you have 15, so you double that. And you could, pressure is also something that needs to be. It costs energy to apply, but you could go higher with your pressure. So all of that is really the autoclave is a pressurized heater. So if you do that at home, if you can change your dishwasher to that kind of setup, you're gonna be good for.
So that's a true sterilization, right?
Yeah. So that is true sterilization. And the other thing is the steam must reach the surface. A lot of times, things you want to sterilize don't have surface areas that are easily reached. So you have to make sure that's a possibility. And then you have the problems of certain things you want to sterilize can't take the heat or can't take the moisture or change. So it only works for certain materials. And here, for example, anything we use goes into the autoclave because it just means you can reuse certain things. If it's glassware, you just put it in. You put this, I don't know, I showed it to a couple students. You put a tape on, and the tape changes the color, and so the tape just is a specific tape that changes color if you reach 121 degrees Celsius at 30 psi for say 20 minutes. And then so you take it out and okay, tape changed, the glassware is sterile. And then I see it on campus, they put all the sterile glassware basically in these cabinets, and then I guess they're sterile inside. There's aluminum on top. You're still gonna see some, not those. Remember DI water?
Yeah.
And that's the same thing. I always wonder about that too. They put everything in, and people grab it. I mean, you take it out, it gets exposed, but you do the best you can. I mean, it's the concentration, and it's also you have usually aluminum foil. You put aluminum foil over the top, so if you have a beaker, it should stay clean. So in cases where you can't apply that pressure, and it's just, I don't think this is too important because you can always use the autoclave. It just means there's other ways. If it doesn't work, it gives you an idea of what you can do if you can't use the pressure or the temperature. And so this is named after a guy who experimented with it, thinalization, and it means you expose your items for 30 to 60 minutes and then incubate it for a day or a 24-hour period, and then do it again. So what this method is trying to do is to give vegetative cells, remaining vegetative cells that survive the 30 to 60 minutes of steam that is not as hot as the autoclave steam, to produce spores, and then the spores to produce vegetative cells. So it's basically in a period of time, over 24 hours, if there are any spore-forming bacteria in there that then still are trying to grow and produce vegetative cells, you would then in the next cycle kill them, and that's really all you're trying to do with this. So you repeat that cycle for 3 days. And that's sometimes used for canned foods and laboratory media, so media we get here. And important is, and that shows up more and more now in every method I show you, it's disinfection, it's not sterilization. So it's clear that this is it's a long method. If you think about having to do this for 3 days, it's a lot. You have to follow the steps through for a lot longer, and it doesn't sterilize. But in some cases, you have no choice. Another way of, if you boil water, you can destroy most non-spore forming pathogens. It's just another method. So you would have, again, disinfection. You don't have sterilization because you would not kill spores. So you basically destroy the non-spore forming pathogens, or pathogens but not the spores, would be the better explanation for this. And then the difference here is pasteurization. Somebody asked me before, so what's the difference, or if you look at what happens in an autoclave and then through pasteurization. And so this method is a lot milder. And it's usually applied to liquids, and you probably know it from pasteurized milk products, etc. So you're trying to kill potential agents, and I said that a few times today, without destroying the food flavor or value. And that's always a balance where you have to try to find a way to be as clean as possible, or have a product that's that's not spoiling immediately, but or has a long shelf life, but also doesn't change the product itself too much. And so you would you apply around 63 to 66 for 30 minutes, or a higher temperature for 15 seconds. So there's the flash versus the batch method. So it's not sterilization. It does not. It lowers the overall microbe count, but it won't kill the endospores and some non-pathogenic microbes. So even if you would take a milk home and you don't use it and you leave it closed, so there's no way of microbes getting in, eventually the milk would spoil, and that's because you have some of those non-pathogenic microbes in there growing eventually. And this is just I think this is an example. It's in your book. A pasteurization apparatus for milk. And then in comparison to the boiling water or autoclaving or pasteurization that's applied to liquids, dry heat needs a lot higher temperatures than moist heat. So you can incinerate, and that's usually through a flame or electric heating coil. There's, I guess, electric heating coils where you just use your loop and you heat it up that way. And you can also use dry ovens, and they go up to 180 degrees Celsius to coagulate proteins. So they're affecting the proteins. It's a simple way, but again, how do you could look at what we're using. You wouldn't want to apply dry heat to any of the plastics we're using. Yes.
Have you ever put a hamburger in the oven? Like, have you baked a hamburger before? Like,
you mean in a oven?
Like a regular oven. Because I guess the fat or something comes out, and I think it coagulates. It's like a little layer around it. Is that kind of what that does? Is that like the coagulation of maybe fatty lipoprotein?
Anybody working in the hamburger business?
You don't always want to even if you fry it, you can see it too. But baking, you'll get like a film around it.
What's the film look like?
Kind of like jello. It coagulates.
And then when you let it sit, it
Probably blood.
Yeah, you should try it one day. It's great. It's really good. It's tender, but then you got to get over the fact that there's something or you have to scrape it off or something. Yeah. Anyway.
Right.
But I mean, because you're killing the pathogens, if you bake it over a certain temperature for a certain amount of time, right?
Yeah.
That's probably what it is. I think.
But
I feel that.
I was just thinking in terms of what you would see, I would assume it'll be more of the fat, or it's just
Is it pushing?
I have to look at a picture.
Do an experiment.
You should.
If we ingest the endospores, do they produce bacteria inside us, or do they just go through without hurting us?
Sorry?
If we ingest the endospores of bacteria, will that hurt us, or do we just pass them through?
Who wants to answer that question? Clostridium. So there's an endospore we could ingest. Yeah, so you would.
The endospores itself?
Yeah, so depending on where, with Clostridium, we had a couple of them, but if you get them in wounds, that's a different story. But you could, you would basically create, you get the endospores, for example, from the canning, what we talked about, and so they're in anaerobic, and then you would expose them in some certain parts of your body to conditions where they start to produce vegetative cells, and then those produce the toxins. So if you could have an endospore going through your system, which I don't know if that happens, but if you would, that wouldn't really be a problem. It's the toxins that are produced by the vegetative cells that are causing the problem, or causing the disease. Your households are worse than mine, that's all I can say. Cold is another one. So we had heat, Cold, where are we here, 26, that should work out. Cold is another one, and everybody puts food in the refrigerator and also in the freezer. What would you think if I ask you, just what makes sense to you? I mean, we freeze things. The problem is we also, you can also preserve microbes in the freezer. So they, in the laboratory, they use freezers to take a culture and then revive it later on. So it really doesn't do that much. And the other thing is, aren't there? That there are. Could you draw a graph of the microbes that really like this kind of condition? And what are they called? Yeah. So they would actually be really happy if you put them in there. So it's not really that and you know that, I mean, things spoil in the fridge all the time. Freezers is better, but it just means the microbes are inactive as much as everything else. So you're not really generally you're slowing the growth, but you're not generally, you might not kill what you want to. So it's not preserving. I mean, it's preserving it just like you're preserving the food, but it's not killing the microbes. So here you would call that microbiostatic. Desiccation is basically removing the water from cells. So that means you have metabolic inhibition. It's not very effective again. When water is reintroduced, they may grow again. So think of endospores. Obviously, they're happy to. The cells are happy to change into the endospore under those conditions. A common method for preserving microorganisms in other cells is actually freeze drying. So because what happens is in freeze drying you remove the water and freeze, and a lot of times when you have water enclosed in cells, then you get these ice crystal formations, and that's the problem. So if you remove the water first and then freeze, it actually enhances. So those are a lot of those methods we're talking about right now are applied for short periods of time. They work because we don't have to be working in sterile. We don't have to live in sterile conditions, but they don't produce sterile conditions like some of the physical, like the moist heat does, or the high dry heat does. We don't have time for this today. Oh, you can. You can take a short break and think about this. So microbiocidal. What are those